Hello and welcome. In this video, I'll be covering section 6.1 from our book, which is over trigonometric functions of acute angles. My goal for you by the end of the video is to be able to determine the 6 trig ratios for a given acute angle for a right triangle, to determine the trig ratios for a 30 degree, 45 degree, and 60 degree angle, to, with the use of a calculator, find function values for any acute angle, as well as given a function value of an acute angle, find the angle. And lastly, to, from a given function value for an acute angle, find the function values of its complement. So before we jump into any examples, let's go ahead and talk about some of the basics of right triangles as well as their acute angles. So first off, an acute angle is any angle that has a measure that's above 0 degrees but below 90 degrees. After all, a 90 degree angle is what we would consider a right angle. And usually our angles are represented using Greek letters such as alpha, beta, gamma, theta, phi, as just a few examples, but there's even more. But for whatever reason, mathematicians just kind of have decided that Greek letters differentiate itself enough from the trig that makes it such that they stand out a little bit more. It doesn't necessarily mean they always have to be utilized with Greek letters, but it often is something that if you see a Greek letter, such as any of the examples here, the most common ones for the most part are alpha, beta, and theta. Probably theta will be the one you guys see the most, but your book does like to throw phi in there every once in a while. Not that, again, that matters a whole lot. It could just be A's, B's, and C's with capital letters if we really wanted to. But anyway, if we consider some of the parts of a right triangle, hopefully this is a quick review session, but the longest side of a right triangle is what we call the hypotenuse. It happens to always be across from or opposite of the 90 degree angle, which as you can see in this picture is denoted with this box in the bottom right. And then the other two sides called legs, kind of depending upon which angle you use as a reference, are either going to be the opposite or the adjacent. So as you can see with this picture here, they've labeled theta to be this bottom left angle. So across the shape we call that the opposite, and next to it we call that adjacent. Technically the hypotenuse also happens to be next to that angle, but again we've already called the longest side, or the one across from the 90, the hypotenuse, so kind of leaves the other side must be what we're considering the adjacent. Now if I were to switch my attention to the other angle up here in the top right, let's say I were to look at this angle up here, notice now what would be considered the opposite would be the bottom side, whereas the far right side would be considered the adjacent. Hypotenuse still would be in the same spot. So it kind of depends on where your angle is and what you're going to use that will help you identify what the opposite or adjacent happen to be. Now to talk about some of the trigonometric ratios. So the trig ratios we're going to be dealing with all are just ways to relate the different side lengths of a right triangle. And then we'll go quite a bit in depth the remainder of the semester as to how we can utilize some of these things in various ways. So we'll start with the basics. Here are the 6 different names of the trig ratios. I'm assuming most of you probably will recognize the first group there of sine, cosine, and tangent here at the top of the screen. So sine, cosine, and tangent represented with the 3 letters as you can see in the parentheses after. Now what's more than likely new are this second line, or is the second line of functions called the cosecant, the secant, and the cotangent. And we'll do a few examples of that here in this video of how we could find them, but essentially those 3 functions are just the reciprocals of the ones that are directly above them. So like the cosecant is the reciprocal of the sine function, secant is the reciprocal of the cosine function, and cotangent is the reciprocal of the tangent function. And you can kind of see that here at the bottom half of the screen, where notice the sine ratio that I have here, where it's the opposite of theta over the hypotenuse, the cosecant of it, that function, if it's the same angle, notice it's referencing the theta on the inside, and sometimes you'll see parentheses around that. You don't necessarily have to see parentheses though, but it is whatever directly or whatever is directly after that name of the function, so whatever the three letters are, that happens to always be an angle. So you can always kind of think like what goes inside of trig will always be an acute angle. I guess it doesn't have to be acute, but for this section it will be. And then from there, what I get back is some ratio of sides. So notice it's a number that would be over another number, which even if the hypotenuse was a 1 and we could reduce it to where it looks like a single number, I still would have the ability to write it as a ratio. But anyway, as you can see with the connection here, the sine ratio being opposite over hypotenuse, its cosecant ratio then would be just the hypotenuse over the opposite. So if I can get the first three functions that we're familiar with, sine, cosine, and tangent, getting the other three functions is not overly complex. I would just need to potentially flip and then maybe rationalize if I ended up having any radicals get involved. Now, an acronym you might recognize that associates with this or helps us maybe understand or remember what those ratios are is this phrase SOHCAHTOA, which also sometimes can be written as something that looks like this at the bottom of the screen here, to help a little even more with what the ratio would be. So SOHCAHTOA, again, is the first letter is just representing your sine, cosine, or tangent in that order, and then the O, the A, and the H, depending on which trio of letters we have. The O stands for opposite, the A stands for adjacent, and the H in each of those cases stands for the hypotenuse. So again, the acronym can be helpful, or you can just, through brute force, try and memorize which ratio goes with which function. So without further ado, let's go ahead and just get one example under our belt here. Let's go ahead and just do part A, where it just wants us to list out the 6 trig functions, or at least the trig ratios for each angle. So theta in this case being the bottom right angle. If I were to go ahead and label on our picture, we know that across the shape should be the opposite. Next to it must be the adjacent, and the hypotenuse always is the longest. So for theta, at least, I would have the O, the A, and the H go in those spots that I just added to the picture. So if I wanted now the ratios of each, I'd have sine of theta should equal the opposite over hypotenuse from SOHCAHTOA. So the opposite being 12, the hypotenuse being 13. And while we're doing it, let's go ahead and just figure out what the cosecant is, since all it is the reciprocal of that. So if sine is 12/13, cosecant would be 13/12. Similarly, we could go through and do the cosine. So cosine of theta for this example would be the adjacent over the hypotenuse. So that would be the ratio of 5/13. So its reciprocal secant, which again, these and the right are going to be some of the less familiar or new functions for you. But again, all I have to do is just, if I know the cosine, just flip it or find its reciprocal, which is 13/5 for this example. And then the last one, let's go ahead and do tangent of theta. So TOA, that would be the opposite over the adjacent. So that would be the 12/5 ratio from our triangle. So its reciprocal function cotangent must be a 5/12. And if we wanted to do the same thing for the alpha, I think I'll just probably do a couple of these because I feel like we probably get the point here. But if I wanted to go through and just do a couple of the alpha angles, notice now if I did sine of alpha, I need to go back to my shape, and instead of having my O and A's in the spots that I currently have them, I now need to flip-flop them, because across from the alpha should be now the opposite side. So notice now my O is where the 5 is, and the A is where the H is, and now we should be able to go through and figure out any of those trig ratios. So just wanted to at least model one or two of these. Go and switch back to the right color, and go ahead and do like sine of alpha. So sine of alpha, as you can see here, would be the opposite side 5 of that angle over the hypotenuse, which still is 13. That was a weird looking one. There we go. And let's go ahead and just do maybe the original 3. So cosine of alpha would be then 12/13. And tangent of alpha, if I needed it, would be the opposite over adjacent, so 5/12. If we needed to do the other 3 again, it would just be take those same ratios and flip them. So cosecant would be 13/5. Secant would be 13/12, and cotangent would be 12/5. So kind of notice that once I switch from one angle to the other with the 2 acute angles, once I changed my reference from being theta to then being alpha, Notice, again, I got a lot of the same ratios. In fact, I got all of the same ratios, but it was for a different angle. So that inside part, this here, where I had a alpha inside of that sign, but here notice I have a theta inside that one. It's definitely using a different reference, which is why it's creating a slightly different ratio. So we'll do one more example relatively quick just to try and hammer that point home. Notice this one, it's giving us a little bit different given info at the very beginning. It's not giving us a picture to utilize. Now it's just giving us some specific ratios. And this again is just a different way of representing the same thing. So this notation of 1 divided by something for this specific section or chapter isn't going to be overly helpful, but this is something that will come back around here later on in the year, where utilizing those or remembering that cosecant would be the same as 1 over sine, or vice versa. 1 over sine you could turn into a cosecant. That will become something that will be a little bit more useful a little bit later. So for right now, it's just kind of be familiar with when you see this notation where it's 1 over something, that really just turns into its reciprocal, or that's the way of saying it's the reciprocal of this as a way to do it. But anyway, if we look at the examples down at the bottom, it's just representing some of the ratios that I would know. So sine of theta is, in this case, 4/5. So just like we did on the last example, I can now say that cosecant of theta must be its reciprocal 5/4. Just like if they gave us cosine of theta as 3/5, as they do, I should be able to do its secant function for that would be 5/3. And the last one, if tangent is 4/3, then its reciprocal cotangent must be 3/4. So again, hopefully this is seeming relatively easy. I think that is ultimately the intent, is to try and make this as easy as possible. So again, just remember reciprocal functions, which one goes with which. The way I always remembered is if a function started with C, its corresponding reciprocal function will start with the other letter S. The two tangents, though, happen to go together, so it's cosecant goes with sine, secant goes with cosine, and again, you can kind of see like when one starts with S, the other one will not, or it will need to start with a C. So it's either a C turning into an S or a S turning into a C for the first letter, if that helps in any way, shape, or form. But hopefully we can at least connect that the two secant functions, either secant or cosecant, are the reciprocal of the original sine or cosine. Now another thing to note with right triangles, we do have a theorem that I hope we all remember from our past that we could utilize. That theorem happens to be a squared plus b squared equals c squared, otherwise known as Pythagorean theorem. So with this one, notice the picture is given us only 2 out of the 3 sides, so this one's going to require us to do a little bit of legwork. So let's go ahead and just solve for that a. The a in this scenario is going to be this result of doing the square root of, and if you think about it, if I have the longest side, in this case being labeled as a 7, the only thing I can really do when I square it is take away from it, otherwise I would get a larger number, which we know we can't get. So for this one, I'm just going to go ahead and jump straight to how I would type this into a calculator, which would be 7 squared take away 6 squared, which really we don't necessarily have to have a calculator for. That would just be 49 take away 36, which should give me a 13, and then I would just make sure that I keep the square root on it. And instead of converting that to decimal, I'm going to go ahead and just keep that in this exact format, which is radical form of the square root of 13. If I could maybe simplify by like doing a factor tree and pairing something up, I'd go ahead and do so at this juncture, but square root of 13, since it's a prime number, is not really going to be able to be simplified. So now it just wants us to figure out what are all the 6 trigonometric ratios for this angle beta. So beta is this bottom left angle here. So notice I've got the opposite side would be across the shape, the adjacent side would be the one next to it, and the hypotenuse always is the longest side, which we already had labeled as a 7. So now if I go through and identify each of these ratios, sine of beta will equal the opposite 6 over the hypotenuse 7. And while we're doing it, may as well just do the cosecant of beta, which is just its reciprocal 7/6, as we've done with the last 2 examples. Trying to speed this up a little bit more, cosine of beta in this scenario is going to be the a value I just solved for, square root of 13 over the hypotenuse 7. And its reciprocal secant of beta should then be 7 over a square root of 13. And at this point, I'm hoping that there's something that kind of jogs your memory banks from your past, is I'm not supposed to leave these radicals on the bottom. So this will require us to do a rationalized step, which I'm going to go ahead and show the work for at least once, but I think we can probably come up with a little shortcut where if I have a radical on the bottom, it's just basically going to be something that moves to the top because I'd multiply top and bottom by that radical, and then the bottom will now just leave the number without a radical, because after all, multiplying something by itself is the same as squaring, and if I square a square root, the square root should go away. However, it should leave the number. So notice in this case I have now 7 rad 13 over 13. If I could reduce the 7 and the 13, I would, but neither of those have anything in common other than a 1, so that's as good as that will get. But anyway, let's go ahead and move on to our last pair. Tangent of beta would be the opposite over the adjacent, so that would be a 6 over that square root of 13. And I think we can see that pattern happen again here, where it's just rewrite the radical on top and then drop the radical on the number that's on the bottom. If there happened to be another number on the bottom, I would actually multiply it. But again, we didn't have to worry about that here. And since we have that one, I'm going to go ahead and do the cotangent ratio, which it's actually easier to flip the first version of that had the radical on the bottom and just say that that would be a square root of 13 over a 6. And notice I don't have to rationalize that. Whereas if I would have gone with the newer version, the one that I did rationalize, then the denominator would have a radical again and I'd have to rationalize the second time. So having it listed out kind of as the two different versions, but again, making sure that I'm going to the final answers here for each one of them. Right, making sure that those are my final answers. Having the ones in the middle like this one or this one here for secant, having those ones, notice it's kind of nice if I needed to do the reciprocal, because that actually moves from the bottom to the top when it, I guess at least with reference to that number that has the radical on it. Alright, so another thing that we could encounter when dealing with right triangles is this concept of identifying whether something is similar or not. So recall from prior classes that we have similar shapes requiring all of the angles that correspond with one another to be congruent or the same size, but potentially having all of the corresponding sides have a different size. However, they do have to make sure that they maintain the same ratio the entire time. And you may have called that ratio a scale factor when it was all said and done. So the way that we could determine whether two things are similar is first identify whether our angles are matching up. So notice with this one I have alpha and alpha, so both triangles at the top left have the same measurement, because if alpha, say for example, was 60, I'd actually be able to put 60 in both of those spots. So that would have an identical angle. Same thing with the bottom right. Notice they've been labeled as beta in both shapes, and then I do have the 90-degree angle. So for sure, yes, the corresponding angles are all identical. And as we can kind of see, the size is definitely different, so more than likely this is similar, but let's just double check all of the ratios. So the ratios I could come up with, I could go big shape divided by small shape, or vice versa. I think it's going to be a little easier to see if I go big divided by the small. So if I go ahead and write some of those numbers down, it would be 20 over 5 for sure corresponds with each other, which reduces to a 4. So as long as all the other ones in the same corresponding order reduce to a 4 in some way, shape, or form, then I can go ahead and say, yes, these are similar. So let's try another pair here. Looks like between alpha and the 90-degree angle, that happens to be a 12 and a 3. So if I did 12 divided by 3, we'd notice that also turns into 4. And do one last check for the last one. The side between beta and the 90-degree angle is a 16 on one, a 4 on the other. So 16 divided by 4 also gives me 4. So since all three of those agree, it technically gives me the scale factor from the big shape. Actually, no, it's more from the small shape to the big shape, because I would multiply it by 4 to scale it up. So that does give me the scale factor is 4. But again, because all of those are the same, I can go ahead and say, yes, the triangles are similar. And I probably should have named each of these triangles just so we could actually come up with what the similar statement would be. Similar, that symbol, if you ever were to see it mathematically, is just like a single squiggle line. So it's kind of like the top part of a congruent sign. It just doesn't have the it doesn't have the equal underneath it. So if you ever see just one single kind of squiggly line like that, that just means that the shape is similar to the other shape with whatever that reference might be. It doesn't have to be triangles, but for this chapter, we're going to have to, or happen to, make that more of a connection with triangles if it ever shows up. Honestly, in this class, we don't really explore that concept a whole lot, other than I do have the ability to take maybe some ratios from bigger triangles and reduce them down and turn it into smaller triangles if it makes the ratios easier to compute. So if you notice that you could scale something down, I might recommend doing it, if they all have something in common, in other words, because doing your trig ratios with like this 3, 4, 5 triangle that's down here on the bottom left would actually prevent us from having to reduce all 6 trig ratios as I found them. So if you can reduce one time at the beginning, I guess that technically could be one way of making this a little bit easier in the end, at least for your final answers for each trig ratio. Alright, so let's go ahead and talk about some of these special right triangles that we have. So one of the special right triangles that we can talk about is this one that's called the 45-45-90 triangle. And oftentimes books will actually utilize the letter T. These books that I've encountered in my life usually put T and T for the two legs, because if they have two angles that are the same, then the two sides need to be identical. And then the hypotenuse would just be that side length times the square root of 2. So notice with this one on the outside edges, they labeled the two legs as 1s, which then means the hypotenuse must be 1 times square root of 2, hence the square root of 2 that's on the outside. Now, as far as coming up with the ratios for each of these, sine of 45 degrees, I could reference either one. I'm just going to focus my attention on this bottom left one. So if I call that one my 45-degree reference, the opposite would be 1. The hypotenuse would be square root of 2. So it would be 1 over the square root of 2, which I can then rationalize. And it will always turn into a square root of 2 over 2. So it doesn't matter how big or how small the triangle happens to be. If you have a 45-degree angle and it's a right triangle, the opposite and hypotenuse ratio will always reduce down to a rad 2 over 2 somehow, some way. Notice our cosine ratio ends up kind of being the exact same, or in fact it is the exact same, but I'm referencing technically a different side. It would be my adjacent 1 over the hypotenuse rad 2, so just like before, 1 over rad 2 gives me the same ratio, rad 2 over 2, if I rationalize it. And so basically, again, any size triangle, if I have a 45-degree angle and if it's a right triangle, the adjacent over hypotenuse sides also have that same ratio of rad 2 over 2. Then tangent of 45 degrees would be my opposite over my adjacent, which would be a 1 over a 1, which is conveniently going to turn into just a single 1. Now, as far as like why would I care about the T, T, and T rad 2 situation, I'm going to go ahead and just kind of model a couple here off to the side. Let's say I had a triangle drawn like this, knew a 90-degree angle, and I've marked the other two to be congruent, so they have to be 45 degrees. Let's say I knew that this side over here was 5. I could then say that the other leg must be 5, and then the hypotenuse must be 5 square root of 2. And notice that's just following that pattern of once I know what T is, now I should be able to label all three sides without having to fall back to like Pythagorean theorem. Now the one that's a little bit more complex version of that, let's say I draw a very similar triangle, mark the two sides here, but let's say I maybe had the hypotenuse as, I don't know, let's just throw a number out there like 7. Going the other direction, I would actually need to think like, well, 7 is in the spot of T square root of 2. So to solve for T, I would take the square root of 2 and divide it from both sides. That way they cancel out. And then I would have to rationalize. So for this situation, I would now have T being equivalent to 7 square root 2 over a 2, which then coincidentally would just be the side lengths for the two legs that were across from the 45-degree angles. So having that ratio memorized, the idea of the two legs being labeled as T's and then the hypotenuse being that number times the square root of 2, or T rad 2, can help simplify or speed up that process of solving 45, 45, 90 triangles when it's all said and done. The other special right triangle we have is what's called the 30, 60, 90 triangle, and oftentimes books with this one use a slightly different letter. In this case, I'll use the letter W because that's pretty consistent from book to book. But if I had this shorter side, so the one across from the 30-degree angle, labeled as W, the hypotenuse is always twice whatever that number is, so 2W. And then the longer leg, this one over here, is always going to be W times the square root of 3 as far as the ratio of sides to each other. So once again, if I were to now go through and identify all of my sine, cosine, and tangent ratios, depending on the angle I'm looking at, for the 30-degree angle, I'd focus my attention on the top angle, so that means that I would have the opposite be 1 and the hypotenuse be 2, so I'd end up with my sine of 30 degrees just being a 1 over a 2, or 1/2. Cosine, on the other hand, would be the adjacent over the hypotenuse, so that would be a square root of 3 over the 2. And then my tangent would be a 1 over a square root of 3, which I would then need to rationalize, and it would turn into a square root of 3 over a regular 3 if I multiply top and bottom by the square root of 3. Now if I change my reference to the sine of 60 degrees and cosine, and if I change it just to that angle, 60 degrees actually, the sine actually would turn into basically the same ratio as cosine, because now the rad 3 is the opposite and the 2 is still the hypotenuse, so rad 3 over 2 is that ratio. And we'll talk a little bit more about why that works, but that technically is kind of an introduction, and this actually showed up a little bit earlier. I could have mentioned it at that point, but the co-functions, so notice sine and then cosine, key part of that being the co in front. So the co-functions of each other, if I switch from one angle to its complement, or the other angle in a right triangle, they always happen to hold the same ratio. So we'll explore that again a little bit later in the video. Similarly here, if I know that the sine of 30 degrees is 1/2, if I switch to its complement 60 degrees, its co-function, cosine, should also be the same ratio of 1/2. But again, we could also just look at where is the 60-degree angle. It happens to be the bottom right one. The adjacent is that side 1. Hypotenuse is 2, so it turns into that ratio 1/2. And then the last one's tangent of 60 degrees. That would end up turning into my opposite, which is rad 3 over a 1, which technically I could just simplify and call that just the square root of 3. So again, when it comes to drawing maybe some of the situations that I would be able to use this triangle to my advantage, if I said there's my 30-degree angle up here at the top and my 90's here, if I knew, say, the bottom edge, let's go with maybe a relatively easy number like, I don't know, 4, the hypotenuse of that would have to be twice as much of that, which would be 8. And then the longer leg, or the one across from the 60-degree angle, would just be that shorter leg, 4 times the square root of 3, to be able to scale it up a little bit. So notice if I know that bottom edge, it makes this not too tough to fill out the other two parts, and I didn't need to use Pythagorean theorem at all. Now let's say we had a different situation. Let's say maybe I knew the hypotenuse. Let's say it was like 20. Well, if I needed to go backwards, the shorter side, I guess I should label where the 30-degree angle is. So if I still kept the 30 degree at the top there, that shorter side, or the one across from it, should be half as much as the hypotenuse, so that would be 10. And now that I know that edge, I should know the longer leg must be that number times the square root of 3. So again, the first two examples that I did there, relatively straightforward. This last example, let's say where I have the 30-degree angle up here again, let's say I knew this side over here was, I don't know, let's go with like 8, just for the heck of it. So let's say that side was 8. To go backwards, I would actually have to do something similar to what we did with the 45-45-90, where I would set W rad 3 equal to 8, divide the square root of 3 off, and then rationalize, which would turn into 8 rad 3 over 3. So that would be my bottom edge here, 8 rad 3 over the 3. And so if I double that, that would turn into just 16 rad 3 over that 3. So that's the toughest version. That's the toughest type of question with a 30-60-90 triangle to solve, is if they give you that longer leg. But notice, where there's a will, there's a way. We just had a couple of ugly side lengths that ended up resulting just because 8 didn't have that rad 3 already on it. I guess technically we can make that a little bit worse if we chose a slightly more terrible number in that spot. So let's say it already had a radical like something like rad 17. That would be a little bit tougher to try and solve, but we technically still could do it. It's just the other two sides are also going to be not so nice numbers. So again, just wanted to kind of model the why would I want to know those ratios of W, 2W, and W rad 3 for those three side lengths. And again, the whole reason would be is it actually simplifies the solving for the outside edges without really needing to, 1, do anything with trig, but also 2, I didn't need to use Pythagorean theorem either. So again, there's a few examples that hopefully you find a little bit useful. Alright, so let's go ahead and work through a relatively quick example here of a 30-60-90 triangle application. And we'll kind of see how we don't necessarily have to utilize some trig for this specific triangle. But let's say we wanted to shoot off a firework and not have it explode directly above our heads. We wanted it to kind of explode somewhere off in the distance. We would probably need to shoot it off at an angle other than 90 degrees with the ground. So if we shot it off at 60 degrees, that should travel away from us if we're sitting on the other side of it. And if I were to go ahead and say, let's draw that situation, it would be a 60-degree angle going up. Let's say we call this one the 60-degree angle. Not that that's perfect to scale, but I think we can still get the idea. And it says that it's going to travel a horizontal distance, so that should be this bottom edge of 390 feet. So 390 horizontally, so that kind of is going to be popping directly above the ground there, and it just wants to figure out how high up in the air will that actually be. And we can go ahead and try and figure out what that would equal. So if we go ahead and try and come up with what that side length should be, notice I would have the 30-degree angle is the one that's up here, so technically I know the shorter edge, so this longer leg should just be that number times the square root of 3, which I could then type into the calculator and see what that would equal. So I'm going to go ahead and just model that situation here, bring up a calculator. I'd have that side length 390 times the square root of 3, which would just be the second of the x squared button. Put 3 on the inside and go ahead and just press enter, and it turns into 675 feet and about a half, so 675 and a half if I were to go with that. So equals about 675.4. It does say round to the nearest foot, so I'm actually just going to round that down and just call it 675 feet approximately. Alright, so moving on to the next concept. The acute angles that we have in these right triangles, technically we have a couple of different ways that we can represent it. Probably what you've been most familiar with prior to this class is just being able to utilize decimals in the event that it didn't come out as like a perfect degree. However, there are some situations and fields where we might want to be a little bit more clear or direct with how we could communicate maybe a not so nice decimal. And what that method is called is degrees, minutes, and seconds. And I'm going to assume that you probably recognize the words minutes and seconds, and I hope that if you think about those words that the number 60 gets involved. But ultimately what we can do with that information is say that if a degree is our whole idea, then minutes, in terms of like kind of similar to time, there would be 60 minutes that would make one full degree. So notice one full degree here is equivalent to 60 total minutes. And the way that we represent minutes is with an apostrophe. And then seconds is more of like a quotation or a double apostrophe. And notice there would be for each minute 60 seconds that corresponds with it. So again, very, very similar to, in fact, it's the exact same as how we interpret how those connections between minutes and seconds and hours would go. It's just instead of talking hours, we're actually talking degrees. Now, if I actually wanted to figure out how many seconds are in a degree, well, if there's 60 seconds in a minute and then there's 60 minutes in a degree, then shouldn't it just be whatever 60 times 60 is? So that would be 3,600 seconds. So 1 degree is always equivalent to 3,600 seconds. And actually it's those two numbers, the 60 and the 3,600, that we'll take advantage of when it comes to converting from one form to another. So this first version here, if you can kind of see here, if I had 61 degrees, 27 minutes, and 4 seconds, I basically would just take my minutes part, put it over 60, and then I would take my seconds part, put it over 3,600, because ultimately what I'm trying to do is turn everything into some version of a degree. And each one of them will just come back as decimals of a degree. And then I basically just add those results together, where notice the whole number part just stays the whole number part, 61. The other parts, because they're going to be proper fractions, will turn into decimals that when I add them up won't really take that 61 and change it at all. So the number of degrees that I have initially will always stay the same. It's the parts after it that will turn into some version of a decimal. So if I were to actually add these up on a calculator, it would turn into 0.45. And I can show you how this all will work here just in a second on the TI-84. But as far as like other things that we can do, we actually have the ability to type this in exactly as it looks, and I'll show how that would work as well. And all of those happen to be inside of a menu where you can kind of see above the button apps, it says the name angle for that menu, or it has the word angle in front of it. So again, I'll highlight it here, the angle right above apps. To open that menu up, I just press second of the apps button, and it opens this menu. You can kind of see it's pretty small, but you can see this menu where it's got degrees at the top, minutes, and then it's got radians, degrees, minute, second, then a bunch of things that this class we don't really explore too in depth, but it would be rectangular to polar R or polar theta is all what those are, and then back and forth. Not that we have learned about polar mode yet. But regardless, in this menu, like the top two, notice, are going to be helpful. That helps me with the degrees, the minutes, and then there's the fourth option, DMS, which stands for degrees, minutes, and seconds. So that's how I'm going to actually convert. Anytime you see that sideways filled in triangle like that, that just means convert into this format. And what's weird to me, and you probably will find this weird as well, is that even though seconds is associated with this, we actually don't have that in this menu. So to make seconds happen on my calculator screen, what I'll have to do is alpha of the plus sign. Notice right just to the top right of the plus sign, it's got this little quotation mark. So on the TI-84s, I just need to take advantage of, I have to click whatever that alpha colored button is. For my calculators, I believe it's all green, but depending on what your calculator is, if you have your own, it might be a slightly different color, but whatever the color of that key is should get you to whatever the alpha or the numeric or alphanumeric numbers, or not numbers, the letters that are above these buttons that would let you actually like type something in. So in this case, we would just look for the quotation, but it should always be above the plus sign if you have a TI-84 or TI-83. But anyway, we'll go ahead and work through an example or two where I convert one direction but then convert back the other direction, and then I'll show you how you can do that on a calculator as well. So kind of utilizing that, I guess, previous slide with the example that was there, we can kind of see that this is going to be very, very similar to what was written there. So to convert this from the degrees, minute, second format into decimal form, again, notice the minutes is the one apostrophe, and then the seconds is the quotation mark or double apostrophe, however you want to think of it. But ultimately what this is going to do is I keep the whole number part of degrees, so it's going to be 5 degrees plus the how many minutes I have out of the total degrees, so it'd be 45 out of the 60 that it takes to make a degree, and then I have the number of seconds, 30 out of how many it would require to get up to a degree, which is 3600, and then I would just type that in the calculator and see what that would turn into. The other option I could do is actually just type it in exactly as it looks, which I'll kind of model both of those here in just a second. You'll see that the decimal result I get for both of these comes out identical. So let's go ahead and bring up that calculator and just go ahead and maybe clear out what we got on the screen. So I'd go with the 5 degrees, so 5, and then go into that angle menu, choose the first option, 1. Then it was, I already forgot what the number was. Let me flip back really quick here. 45 and then 30. Okay, so 45 minutes, so it would be 45 back into that same angle menu. This time select the second one, or I could just press 2 and it would automatically bring it out to the screen. And then the last one is going to be 30, but again, that's not inside that angle menu, so I just have to do alpha of the plus sign, and notice I have it look the exact same. If I press enter, notice it actually just automatically turns into that decimal form. Now what I had typed in, or what I had previously written down, would have just been, let's just type it in as 5 plus the 45 over 60 plus the 30 over 3600, and it takes us to the exact same result here. So technically I didn't have to bounce in and out of different menus, and it actually was slightly faster to write the second way because I didn't have to go through again and open all these menus up. I just had 45 divided by 60 and then 30 divided by 3600. That was way more efficient to at least type in, even though it may have been a few more button presses. It might have been a little faster just because I didn't have to, again, remember, one, which menu the things were in, but also two, I didn't have to go open it up, bring it back out, and then continue on with the process. So you can do it either way. I'm good either way when it comes to grading these, but ideally, as long as we can represent that we understand that there's 60 minutes in a degree and 3600 seconds in a degree, you can take advantage of that when it comes to the conversions. Now if I go with the other direction, let's go ahead and bring the next problem back up. If I needed to convert 72.18 degrees to degrees, minutes, seconds, the way that we can do that without typing that in or utilizing the DMS conversion is I know for sure the whole number part is the number of degrees. What I can then do is a little bit of side work. So what we do is we would take the decimal part, multiply it by 60. So that's basically, again, since I'm going the other direction, instead of dividing by 60, now I'm multiplying by 60. That's going to give me the number of minutes, and potentially it might have a decimal to it. So if I were to go ahead and figure that out, bring this back up, 0.18 times 60 gives me an answer of 10.8. So we would know that the 10 part of that is now the number of minutes. Now I would take the new decimal, which happens to be this 0.8, and I would multiply it by yet another 60. The reason I don't multiply by 3600 is technically I've already converted this decimal into minutes, so all I need to now do is convert minutes into seconds. I'm not going all the way back 2 degrees. So hopefully that kind of makes sense that I just want to take each of the decimals as I go. The first decimal I had was the 0.18. The new decimal I just created was the 0.8, and now I multiply that by 60, and to show that again, 0.8 times 60, I believe is going to give me 48. Yes, it does. So let's go ahead and say that that would be the number of seconds. So 48 with the quotation after it. Now another way that we could have done the same thing back on the calculator is we could just type in exactly what we had, 72.18, and go into that angle menu again, and just this time, instead of utilizing our degrees in minutes and seconds, we're actually trying to convert into it. So that's what that fourth option is. So I'll just go down and highlight 4, press enter, or I could just press the number 4. And notice it takes it out to our screen. It looks something like this. Once I press enter, it should automatically convert it to exactly what we just got, the 72 degrees. 10 minutes and 48 seconds. So either way, I think probably that's more useful for the calculator to do the conversion into degrees, minutes, seconds, but notice you can do both. And if I go back and actually write down our answer from the previous one, I believe, what was that, 5.758. Let's go ahead and keep that. I already forgot it, 758. Sorry about that. As far as a degree where I don't have any of the minutes and seconds. So final answer for each of those. There we go. All right, so moving on to our last concept of this section, which deals with cofunctions as well as complements. So complementary angles, if we recall from our past, are two angles that add up to 90 degrees. And if we have a right triangle, that should be the two acute angles, always adding up to 90 degrees. And what cofunctions are, notice we have some names that have one part that doesn't have co and then the other part that does. So for example, sine and cosine, right? Again, each of these has a co in front of it, tangent and cotangent, secant and cosecant. Anytime I'm talking about the cofunction, what that basically means is the sine of one angle should be the exact same as the cosine of its complement. So how would I come up with a complement? Well, ultimately I would just subtract it from 90, and notice that creates this or actually more than a trio, it's this group of 6 different cofunction identities that we could utilize, where inside of one function, if I subtracted the angle from 90, it would then match the cofunctions ratio of the other angle. So for example, if I went to like a 30, 60, 90 triangle, which showed up a little bit earlier in this video, we had the sine of 30 degrees was 1/2, so that would match the cosine of 60 degrees, since 60 is its complement for that particular thing. And again, the reason why is the sine and the cosine are cofunctions. So if I go ahead and show an example of that, let's say I was provided all this information. Notice all of this is dealing with the angle 18 degrees. Basically gave me all 6 trig ratios just in decimal form instead of fraction form. No big deal. But ultimately what I can do is say each one of these, the sine of 72 degrees, should be equivalent to its cofunctions ratio for its complement. So if I went ahead and maybe off to the side just show that 90 minus 72, if I were to subtract, is in fact 18 degrees. So the sine of 72 degrees should match the cosine, its cofunction of 18 degrees, its complement. And if we go ahead and look at what cosine of 18 degrees was, it would be the 0.9511. So similar, I can do the other thing, cosine of 72, that must, if I think of its cofunction, which is the sine function, be its complement. So sine of 18 degrees should be the same as cosine of 72 degrees, again, because I'm just changing the angle that I'm referencing. So what was opposite now is adjacent and vice versa. And so now I know that the sine of 18 degrees, which was marked or provided to me to be 0.3090, so I don't really need the extra 0 at the end. It's kind of silly why I typed that, never mind. But 0.309 would be that sine ratio of 18 degrees as it was provided, so that should match the cosine of 72 degrees. So every single one of these you hopefully can see, like, okay, if I have tangent of 72 degrees, that should match the same as cotangent of its complement, 18 degrees, because they're cofunctions. And it provided me cotangents of 18 degree was this 3.0779, so the value of tangent of 72 degrees also should be 3.0779. So hopefully this is kind of making sense, but I'll go through the last few relatively quick. Cosecant goes with secant, its cofunction of the complement, and it said secant of 18 was 1.0514. Secant's cofunction is cosecant. Sorry, that didn't look very good. Cosecant of its complement 18 degrees, and that should equal cosecant of 18 was the 3.2362. And last one, cotangent of 72 degrees should match tangent of its complement 18 degrees. As we've seen for all the other 5, it was the angle 18 degrees was the complement. So hopefully that's no big surprise, and then tangent was provided to be the 0.3249. So utilizing the cotangent, or sorry, not the cotangent, but the cofunctions collectively, not just the individual one, but all the cofunctions, notice it just lets us bounce from one angle to the other angle without having to like completely reset a problem. So sometimes this conversion might be a little bit more efficient, but again, when else fails, just draw a picture, label your sides accordingly, and if you need to change from this bottom left angle to maybe this top right angle, you just hopefully know that these two sides here and here will just need to basically switch with one another. But anyway, that's just the application of cofunctions. We'll deal a little bit more with that when we get into chapter 7 as to how we can convert from one to another. But even that's something that we don't get into a whole lot when it comes down to it. It's just something that's more of a, it's nice that it can work, but it's not really a make or break concept. But anyway, hopefully this video has been helpful. I'm sorry if it got a little long-winded, but it's had just a lot of little things, little terminology that we're going to kind of build off of. So hopefully it was helpful. But as always, if you have questions, just feel free to bring them to class, and I'll do my best to answer them. Appreciate you taking the time watching this. We'll catch you next time.